With that problem in mind, we turn our attention to thin film flows. And this category of flows is rather important for many industrially relevant processes. Some of the processes I'll let you know. So now that particular process has become a bit redundant in the photography industry. So coating of the polymer with a photoreactive film. Okay. Then in the semiconductor industry. So what happens in the semiconductor industry? So you have a base substrate and you want to make gates. Okay, you want to make gates out of this substrate. I don't think you have covered electronics as of now, but anyway, so the thing is, you want to dope one area with, say, you want to dope it with phosphorus, and you want to keep something blank. You want to dope this part also with phosphorus, then you want to coat this with something else, you want to attach wire. So basically, you need to do a lot of masking processes. So you end up coating the semiconductor wafer, so semiconductor silicon in this case. So you end up masking silicon with a coat of what is called as photoresist. So how is that coating done? You take what is called as a vacuum chuck. You might have heard the name chuck when you might have done machining on a lathe. So a vacuum chuck is like the chuck of a lathe. Okay, so this is the silicon wafer and there is a vacuum over here. So that vacuum holds on to the silicon tightly. Then you pour a big drop of photoresist and then you rotate this entire assembly. You rotate it at a very high RPM. Of course, the RPM depends on many aspects, and depending on how much the RPM is and how long the process takes place, you will obtain a thin film of whatever this fluid is. Okay, so that thin film, how uniform that thin film is, it dictates how good that process is. Okay, so thin film flows, typically when we study it in the context of this course, it is going to be between some liquid and air. Well, both are fluids, but air is a fluid with a much lower density than whatever the density of the liquid is. So the density of liquid will be much larger than the density of air. Moreover, typically the viscosity of the liquid will also be much larger than the viscosity of the air. Okay, but the dynamic viscosity, so the kinematic viscosity, that is mu by rho, may be comparable. Okay, that may be comparable, but that's not the point over here. Okay, so let us consider a very simple problem of a thin film falling on an inclined plate. So we have an inclined plate like this at an angle theta, and there is a film flowing on top of this inclined plate. This coordinate system is y and this is x. So let us assume film thickness to be h. We assume that the properties of the liquids are constant, and we will analyze it for a fully developed flow. We will analyze it for a steady flow. Okay, so now this height is equal to h. Okay, so with these things in mind, let us write down the incompressibility condition. So del u del x plus del v del y equal to 0. Because the flow is fully developed, this term vanishes. Hence, this is equal to 0, and this implies v equal to function of x, but v cannot be a function of x. So this will be equal to constant, and that constant will be equal to 0 because this solid inclined surface is impenetrable. That is v equal to 0 at y equal to 0. So because of this, v equal to 0 everywhere. It's the same treatment as we have done for all the other previous problems. So let us write down the two momentum equations. So rho del u del t plus u del u del x plus v del u del y is equal to minus del p del x plus mu del 2u del x2 plus del 2u del y2. Next we can write rho del v del t plus u del v del x plus v del y is equal to minus del p del y plus mu del 2 v del x2 plus del 2 v del y2. So this vanishes because of steady state flow. This vanishes because of fully developed fully developed flow. This vanishes because of v being 0 everywhere. This vanishes because of fully developed flow. This vanishes because of steady flow. This vanishes because v is 0. This vanishes because v is 0. And so we've forgotten to write down the body forces. Anyway, so this vanishes because v is 0. More importantly, this entire flow is actually driven by gravity. Okay, it's a gravity driven process, so we must account for the appropriate gravity body force over here and here. So this is the direction of gravity and this angle is theta, meaning that this angle is theta. So we must decompose it along, so this is going to be theta, so we must decompose it along x and y. So over here, for in the y direction we will have minus rho g cos theta. Okay, this is going to be the body force in the y direction, and over here we will have plus rho g sine theta. Okay, that's the body force in the x direction. So from the y momentum equation we have 0 equal to minus del p del y minus rho g cos theta. So we can write this as del p del y is equal to minus rho g cos theta. We can integrate this to write p equal to minus rho g cos theta y plus function of x. Okay, in general it can be a function of x. And the important thing which is different from the other problems is p over here comprises of the piezometric pressure rather than the static pressure. Okay, so the important thing is it must account for the piezometric pressure. So now when we take the derivative with respect to x, so this will be so minus del p del x will be simply minus df dx. Okay, but anyway, let us proceed with whatever we were writing. This particular expression reduces to 0 equal to minus del p del x plus mu del 2u del y2 plus rho g sin theta. So mu d2u dy2 is equal to del p del x minus rho g sin theta. Now p is a function of, so all this whatever is over here is simply going to be a function of x. Okay, because over here whatever we have written, if we take a derivative with respect to x, okay, then that particular term is going to be only a function of x. So this is going to be a function of x only, and this is going to be a function of y only because of fully developed flow. Hence each of them will be equal to a constant. And in fact, this particular constant we can associate with this term, because this is a pure function of x. This term we can take it on the left hand side. We can write this. Okay, so what is this dpdx going to be? What is this dpdx going to be? dpdx is going to be difference in the pressure across any two cross sections which is in which we have a flow. Okay, suppose it's this cross section and this cross section. So p is a function of y and x. Yes, that is true, but because of the static nature, if the film thickness is constant, whatever the pressure will be at this cross at this point will be the pressure everywhere. So dpdx in this case is p at one point minus p at other point upon delta x, and p at any point is imposed transfers to the wall. So p at the interface is the same at all the points on the film. So essentially what I'm trying to say is dpdx will be equal to 0, because the flow is actually not driven by any pressure, but the flow is driven solely by the body force. So no pressure gradient drives the flow. So no pressure gradient is applied actually. So no static pressure gradient is existing. So this is P atmosphere minus P atmosphere by delta x. So there is no static pressure gradient, but there is a gradient in the piezometric pressure. And that piezometric pressure is manifested through this term. So this term becomes 0. So proceeding with that, d2u dy2 is equal to minus rho g by mu sine theta. So u becomes minus rho g upon mu sine theta y, sorry, du dy equal to this plus c1, and this implies u equal to minus rho g sine theta by 2 mu y square plus c1y plus c2. What are the boundary conditions? At y equal to 0, we have the solid wall of the inclined plate, so u will be equal to 0. At y equal to h, that is rather y equal to small h, I've used small h as the height over here. So at y equal to small h, what is the boundary condition? From the previous problem, we know that the boundary condition, there will be two boundary conditions. The first boundary condition will be a kinematic boundary condition, that is u of the liquid. So if I call it water, u water will be equal to u air. And the second boundary condition will be u mu water du water dy will be equal to mu air du air dy. But if we write down two boundary conditions, everything becomes over specified, because we just want to find out two constants. So we are only concerned with two constants. We could write down the entire set of equations for air also. We could write down such equations for air also. But because we are not solving for the air, not solving for velocity field in air. Okay, and that means that this UA is undetermined. So we can make use of this boundary condition with the approximation that mu A, because it is much smaller than mu W, 3 orders of magnitude to be, that's the ballpark figure, and that implies du W dy. So if mu water is much larger, then du water du is going to be dua much is going to be much smaller than dua dy. And if this is true, then du water dy can be approximated to be 0. So the top surface is essentially behaving like a no shear surface. I mean, no shear stress surface, not no shear. It's effectively behaving like a no shear stress surface. So at y equal to h, the approximate boundary condition would be du dy approximately equal to 0. Okay. So when y equal to 0, u equal to 0, that implies 0 is equal to 0 plus 0 plus c2, which implies c2 equal to 0. And this implies this is at y equal to h. So 0 is equal to minus rho g upon mu sine theta times h plus c1, and this implies c1 is equal to rho g sine theta by mu times h. So combining these two, the final boundary final velocity profile, let me just copy this expression over here. So this implies u is equal to minus rho g sine theta upon 2 mu y square plus rho g sine theta upon mu hy. And if I may arrange this, so rho g sine theta upon 2 mu 2 hy minus y square. So this is the velocity profile. Now there are various things we can discuss over here. I mean, there are a lot of assumptions that we have made. Let us go back and look at each assumption one by one. So assume film thickness to be constant. Can we really assume the film thickness to be constant? Over a small distance, yes, but over large distances, this is not going to be true. Because if you consider this fluid element, this particular fluid element is accelerating in this direction due to gravity. So in general, there will be del u del x greater than 0. It means that the fluid is accelerating in this direction. If the fluid is accelerating in that direction, then del v del y will have to be less than 0 in order to maintain this criterion. So if del v del y is less than 0, it means that there will be a velocity component in this direction. So that velocity component will cause this film to progressively thin out. So the film thins out. So correspondingly, the flow is actually never fully developed, but we can assume it to be fully developed over small distances. Correspondingly, the flow will never be a steady state flow because it's always accelerating. In fact, you might have seen this when you have rainfall on windows. The if this is the thickness of the initial film, so over large distances it starts to thin out. So this thinning is tantamount to having a flow curvature, curvature of the interface. So at a certain point, the curvature of the interface becomes such that the pressure difference between the ambient pressure and this point inside the flow will become quite unequal. So if the interface is flat, whatever we have assumed that the pressure at the interface is the same as the pressure everywhere, that assumption will no longer be valid. Okay. So because of this curvature, the pressure across a transect will differ by the surface tension times the curvature. At a certain point, the film will no longer stay continuous and it will detach. It will lead to a formation of a droplet. And this you might have seen several times in nature. That is, if you just take a sheet of water and roll it on a piece of glass, on a windshield, wherever, you will see that after a while it breaks up. So there's a breakup process, and the breakup into droplet is what happens because of the presence of surface tension. It is energetically more stable for the single continuous film to break up into a multiple droplets. So that is what the physics is. So yes, we have made a lot of assumptions behind this particular problem, and each assumption has a different ramification on the simplification of the problem. The flatness of the interface, fully developed flow, and all this. Okay, each assumption does affect the solution methodology, and this particular velocity profile is at best what is known as a leading order velocity. One small assumption that we have overlooked is this. So let me write it down over here. So mu water du water dy is equal to mu air du air dy. So we have tacitly assumed that mu water is much larger than mu air, and hence du water dy must be much smaller than du air dy. But now suppose I don't have a free interface in an open atmosphere. So this is like a wedge which is open to atmosphere. So this is completely open. So this is in a big room, and you are dropping water on top of this wedge. Okay. But now suppose I have a wedge, I enclose it with another glass plate, and there is a water interface like this. Okay. So at this green surface, so let me just zoom in to this. Okay. So this is the water and this is the air. So if this gap is small h, this gap is say small ha. Okay, at y equal to 0, u water equal to 0, at y equal to h plus ha, u air is equal to 0. So the velocity profile would be something like we have seen in the previous case. There will be a zero velocity again at the top face for air. You have to then solve for the air. So in this case, dua dy will be not, I mean, this condition will not be true because dua dy will have an order of magnitude equal to velocity of air at this plate, which is 0. So this will be velocity at the interface divided by delta y, and delta y is simply ha. Similarly, du water by dy will have an order of magnitude of u interface upon h. So using these things, if if u interface by ha is very large, so despite mu a being very small, dua dy can be quite large, and this will be large if you sort of have a air pump or a blower on top of this water interface. So if you have a blower like this, you will create a large shear stress, and the smallness of the dynamic viscosity of air will be compensated. So this entire term will be non-negligible. Okay. But if you have a large room, if this plate does not exist, so very far from the interface velocity is 0. So you sort of do not encounter a very large gradient in the velocity of air. The velocity of air will be some u interface. Suppose this is the velocity of the interface, and it will gradually become 0 over a very large distance. So if velocity gradually becomes 0 from the interface velocity to a large distance in the room, this HA will be quite large, and so du dy for the air phase will also be quite small. So overall this can be negligible. But if there is a blower and there is another plate and you are blowing air so that there is a large velocity gradient over here, this term will become non-negligible, and then you have to really account for the entire dynamic boundary condition over here. But once again, all this is under the assumption that the interface is flat. If the interface is non-flat, if the interface is non-flat, then you have to take into account separately the dynamic boundary condition. So tau dot n cap is the traction vector, if you recall. So tau dot n cap dot n is the normal uh, component of the traction vector. So this difference, so this is the square bracket implies the difference between the phases will be equal to coefficient of surface tension sigma times the curvature. Okay, and tau dot n dot t vector, where t is the tangential vector. Okay, so that is the tangential component of the traction vector, and the difference between the two fluids will be zero. It's just something advanced, but I just wanted to inform you that these are very simplified solutions. Very complicated solutions do exist for thin film flows. Thin film flows have a myriad of mathematical complexities and physical complexities. If anyone is interested, you can have a look at some of the research articles by Uwe Thiel, uh, Seraphim Kaliadasis. So these are some people who are very renowned in this area and have done a lot of work in this area.